All right. Hello, everyone. Thanks for coming to my talk. My name is Bala Venkatesh. I hope you can hear me all right. Okay. So I'm from the Canadian delegation, but I grew up in Delhi here in Pamposh Enclave next to Nehru Place. If you don't know, I can tell you where it is. All right. So I'm here. I work at Ryerson University in Toronto. Just to give a brief introduction of the university itself. Um, it's about 45,000 students, 3,000 faculty and staff. It's in downtown Toronto. It's probably like if it is in Connaught Place, right? So that's where the university is, just to give you a context. All right. So if you come to visit us, right now we are in the red color building in downtown Toronto, and then by 2018 we'll move to the green color building, which is a new building we are building. I'll show you some shots as well. So if you have not been to Toronto, this is your visit to Toronto on the map. All right. So I run a research center there. The research center is founded by some sponsors. Yeah, no problem. No problem. The research center is founded by some sponsors like Hydro One. I can see here Hydro One, the IESO, and Toronto Hydro. Hydro One, as introduced to you, is the provincial transmission company. Toronto Hydro is the local distribution company like Tata Power. And then the IESO is the system operator. And then we work with many, many other people. Usually we do about 10 projects in any fiscal year, about $3 to $5 million worth of research. So before this, all the talks were very high level, trends, possibilities of using smart grids and so on. Where I come from is a university, so I'll just talk about research projects. I'll talk about new products that we can develop and install and benefit through R&D. So that's really the focus of my talk. I should talk for 15 minutes if I'm not mistaken, and so I'll probably finish by about 4:40 right there. All right, so I'll flip through these slides. So in my center, we do research. We do large-scale testing, and I'll show you some large-scale testing as well. We do education, and we have a little incubator. So today, I'll just talk about 1 and 2. We do research on all of these topics. So should you have interest to do some research with us, by all means, welcome, and you can contact us to do some research. All right. So in Canada and the US, there is a concept of running a network of projects. So at the Center for Urban Energy at Ryerson, we run Canadian network research on energy storage. So this is an $8.5 million network funded by Government of Canada through one of its agencies called NSERC. The total funding is about $8.5 million. It connects about 15 universities across Canada with 27 professors and more than 100 students. All the projects are connected to research on energy storage, specifically on distribution and transmission system applications. It's not for energy storage for your pacemaker or for your flashlight or for something like this. It's grid level energy storage, okay? So that's the kind of research that we do with 15 universities and about 25 partners. So this network is ongoing. The 24 projects are ongoing. The 24 projects are on these four areas. One is on storage, so basic storage technologies. We research on lithium-ion batteries, compressed air, flywheel technology, and thermal technology. I'll show you some products as well that we are making in this. Then we research on power conversion systems specifically meant for energy storage. We also look about research on power systems from the integration perspective. We also work on regulatory and policy affairs connected to energy storage when it connects to grid scale application. All right, so these are the few things that we do on the network. So a brief introduction to you. So a while ago, one of my colleagues spoke about this particular network. All right, so if you visit my center in 2018, these are some shots. You will see my center just for illustration purpose. This is where you'll show up. So this is downtown Toronto, all right? If you meet me, my office should be right here, okay? I'll be smiling at you. All right, so if you look into the center, this is how you'll see the center to be. I hope these pictures appear appropriately from your end. Okay, so this is all about introduction to whom I am and where I come from and so on and so forth. Now, the next part of my presentation is purely technical. So I'll talk about 3 different projects that we have done in the past. These projects are implemented and operational today in a Canadian network, Canadian power network. Is that okay? So the first project is about design of a flywheel technology. So flywheel technology is not new. So if you make a pot, earthen pot, you use a flywheel there too, right? So it's not rocket science. However, we have used this for storing energy. So in this, you spin it at a high speed, store energy, and you can retrieve energy as well. Now, this is an amazing technology when it comes to frequency response or for power quality correction. So this is used for power quality in data centers. So if there is a blip, these units can ensure that there is no power quality issue on the customer side. Is that okay? So this unit is made up of steel. It's a steel flywheel. It's got vacuum and magnetic levitation and a motor generator set right here. So this is a half a megawatt unit, can last for 12 minutes. Now, what this does in this specific application is you have a substation right here. There is a long feeder. In this case, it's a 96 kilometer long feeder, and it is in Alex's company, Hydro One. And then there is a huge wind turbine, which is going up and down in terms of its output. It causes voltage fluctuations. So this flywheel here will go in the opposite direction so that net power flow in the line is constant, and it kills all voltage fluctuations. Is that okay? So this was one of the first energy storage projects that we completed a long time ago, and this is operational today. So I'll give you some shots of its operational work here. So this is the flywheel. I hope you can see the flywheel. This is the flywheel. It's going to be taller than me. It's going to be 3 feet wide, so that's the diameter. And it is buried below grade. It's buried below grade, so it's under this, right under this, okay? So you can see an array of this. There are 10 of these units. So it gives you a 5 megawatt power capacity. So it can go either negative 5 megawatts or it can go positive 5 megawatts. And it can give you real-time help on your network to do frequency regulation. So in Canada and the US, this is a common application. They use flywheels for frequency regulation. It is better and cheaper than using natural gas-fired generators because the cost of having these units and operating them is much lesser. These units can work for about 30 to 40 years. It's just like an electric motor, right? So it can work for a very long time. It's not like a battery or chemical battery that you have a limited life. So this is one of the first projects that we did, can fit into the role of a dynamic energy resource or distributed energy resource. However, you want to expand the acronym DER. So just for your context, to provide a context of size, there are people standing right here, okay? So that's the size in terms of context. So this is implemented. It's been operational for now more than 2 years. It's revenue generating. This is the next project that I will talk about. This project we finished about 6 months ago. It's a project which is implemented in downtown Toronto. So as I told you, this is the campus where I work. This is the building where I work. There is a parking lot right here, okay? So we'll focus on that parking lot. So in this project, there are several stages. The first stage was to build this unit. This is a 40-foot container, 40-foot container. All of this from here to here is lithium ion. And then you have an inverter and a transformer right in, okay? So it provides you 600 volts, 3-phase, 1.2 megawatt hours at 370 kilowatts. So you can take this and connect it to this building. And it will provide backup supply as you wish. This is modular, so if there is power failure somewhere, you can wheel it there and connect it or continue to work. You can supply probably a residential tower with 100 homes or 100 apartments or continue to function. It can provide power quality type work and many of those. So the first part of the project was to design and develop this. The second part of the project, stage 2, was to actually install it and commission it. So this is the parking lot. On this we have the battery, This is a 13.8 kV substation. It's a different voltage system in North America. It's a 13.8 kV substation, and this is my research center. This blue color line is a fiber optic link. The red color line is the power connection. So the power is dispatched into the substation, into the electric network. From here, all we do is control the unit. Is that okay? So that's the setup. So you can see this. This is the parking lot. Our first job was to install the battery system. The second job was to connect it to the electric network. So this connection with the required protection system. The third job was to provide communication network. So all those lines in blue color, the thick line is fiber optic network, the dotted line is Ethernet network. And we have a SCADA system here. So through the SCADA, we control and operate the battery system. Through the SCADA, we also monitor the amount of power going, and we can turn it off every time you wish. So this is the size you can see. It's not a tabletop research. This is the size of the research. This is when it's installed. This smart-looking person is my boss. He's the dean. And rest of my colleagues right there. And this is a shot from the top, right? So this is the parking lot where it's installed. It's installed, commissioning, operational. Why did we do this project? We did this project because if you give this battery unit to a utility, they don't know what are the installation and commissioning tests. So our role was to finish the product and also develop the installation and commissioning tests so that the utilities there, like Tata Power, can use it. So this was a successful project. I'll go to one more project, and that's it. I know all of us want to go to sleep, but one more project and no more, okay? So this is another interesting project. In this, we built a storage unit. The last one was in megawatts. This is in kilowatts. So we built this unit, and this is what this unit will do. If you don't have this unit, the power flowing in this line would be similar to this red color curve, okay? Now if I fix my unit here, fix it, the power flowing up to this point is going to be the red color line. The power flowing in this line here would be a flat green color line. So the energy storage box will automatically program itself so that the power flow upstream is flat. So the utility person, all that person has to do is take the unit, connect it, walk away. The unit will automatically learn, and after 1 week, the power flow here would be a flat line. That's it. So you don't have to do any more mathematics, nothing. There is no central control required, nothing. You just connect it, forget it. So I know there was a Hero Honda advertisement. Fill it, shut it, and forget it. So connect it and forget it. It's very similar. That's the slogan I try to use. We'll see how far it goes. So anyway, so that's the concept in which we developed this unit. This is a architecture just so of all of those engineers in here who are interested. There is a power conversion unit, there is a battery bank, DC bus, some connection and control equipment. So you can address this from the SCADA at the utility as well, just in case if you're interested. All right, I have 2 more minutes, so I'll run along. This is a lab implementation, which we did. After the lab implementation, we built a prototype. This prototype is being installed. This is the truck. This is the unit right here. It's going to be installed on this pole. There it's going up, nearly there. This is my friend Eric Hahn who's going to connect it. So connect it and forget it, okay? Then the next shot is connected and installed. And after you connect it, you don't have to do anything. It'll automatically program itself so that the upstream power flow is constant. Is that okay? All right, so this is the discharge for one day. It'll only have 1 cycle per day so that the battery life is maximized. Okay, so from this time onwards is discharging. From this time onwards is charging all the way to here. Is discharging during the daytime when there is maximum demand. Now, the loading on the system is reduced by 6.14%. So this is showing the transformer load. Certain hours, the transformer load reduces. Certain hours, the transformer load increases. This is primarily to increase the loading during night and reduce the loading during daytime so that it becomes flat. And then the loadability of the transformer reduces, right? So for all of this, I must use smart meter data. I know most of the utilities have smart meter data. So it looks into the smart meters. figures out what the loading pattern is. So this is the red color line is the forecasted, blue color is the actual measured. So we forecast very well. So what this means is we are looking into the residences and we know what you're doing. Okay? We know when you're going to get up and we know when you're going to sleep. So we have that intel on you. So these are the kinds of products that we do. Talking about testing, we do a lot of testing for utilities as well. We have a smart grid lab. Should you wish to create a new product and test it, we can test it as well. Some of the utilities come to us to implement microgrid in the lab and see how it functions. So if the utility connecting this building wants to create a microgrid, we can create that in our lab and test it as well. So those are the things that we do. All right, and if you look to collaborate, please let us know. Thanks very much.